So
Okay.
it was on Monday for
All right, so we're going to begin with problem 10. So group 1 can let me know how you actually did problem 10. So for those of you who didn't get this problem, it goes, a casino has a game with a $1 buy-in. That means you pay $1 to actually play this game. You toss a die, and you earn or lose money based on the following. If it lands on a 6, you get $3. Lands on a 3, you get nothing. Lands on a 1, a 2, or a 5, you lose an additional $1. And if it lands on a 4, they pay you $1 back. Let X be the expected earnings. Create a probability distribution for X. Okay, how did you actually do that?
Okay, so first we have to calculate like the net earnings since it's $1 to play the game alone.
Okay, so so it's your net earnings. What were they?
So you can either lose $2,
Losing $2 was a possibility. Yeah.
lose $1,
Losing $1.
break even, so 0, and win $2.
$2. And we know that because you pay $1 to even play, so you've already lost $1 up front. So if you gain $3, as in the first case, you'll only be up by $2. If you get nothing, that pretty much means you've just lost $1. If you gain another $1, that just means you're back to where you started. And in the worst case scenario, you can actually lose an additional $1, so you're down $2. So our X has these values. You can have -2 earnings, -1 earnings, 0 earnings, or 2 earnings. And what is the probability of each of these?
So the probability of losing $2 is 1/2 because it says if it lands on 1, 2, or 5, that's 3 options out of the 6.
Right. So there are 3 out of 6 ways to get a 1, a 2, or a 5. So that's 1/2 is the probability that you'll actually end up in that situation. Losing $1?
It's just 1/6 because it's landing on 3, which would be 1 out of the 6 options. 0 would also be 1/6, and 2 would also be 1/6.
And by the way, now I didn't explicitly mention this last time, but I think based on how we defined it, it should be kind of obvious. Once you write down all the possible values and you put these in a probability distribution, of course the sum of this must be what? It must be 1, right? Now that's going to be useful if there's a situation where they didn't tell you about all the cases. You can kind of figure out what you need to fill in for the probability for the cases that they didn't tell you about. Because the sum of probabilities must be 1. This is our axiom. We hold that to be true all the time. So that is the probability distribution for earnings. And that was part A. Okay, so part B. How much money do you expect to win on average? And follow up, is this game worth playing? You went to the casino and you saw these rules describing a game. Would you want to play such a game?
So the average winning is basically the expected value of X. So we would use the formula X subscript 1 P1 plus X subscript 2 P2 and so on. So we did negative
1, 2, 3, 4.
Yeah.
So X sub 4, sub 4. So this would be?
It was -2 times 1/2 plus -1 times 1/6 plus 0 times 1/6 plus 2 times 1/6.
And that equals?
-5/6.
What is that roughly as a decimal?
Around 83 cents.
So that's around 83 cents. A loss of 83 cents.
Yes.
Now, that is the average that you will gain from playing this game. You'll lose 83 cents on average. Now, is 83 cents an actual possibility of earnings? Well, no. But what that actually means is in the aggregate. Right? If you play this game a lot of times, you can expect to lose pretty much 83 cents for every dollar you put in. So if you play this game 100 times, you're going to be down $83, right? So the more you play, that's how much on average as a percentage that you're going to lose. So you lose 83 cents in a dollar. When playing many times. Now, this is actually a lot more sound than you would think. It's not just a matter of, oh, you did this probability problem and this, we did these random calculations and we get this number and okay, that's the answer to the problem. But businesses and empires are built on this, right? If you think about it, why would you open a casino as a business, right? Why would your business model be, you know what? I'm going to put up all this money and someone can just walk through the door, roll a dice, and take all my money and walk out the door. How is that a good business model, right? It's not a good business model because yes, you can lose, but the probability works out on the aggregate, on the average. Yes, a guy might walk into my casino and win $10,000 from me, but if 1,000 people walk into my casino, they're not all going to be winners, right? In fact, with this game, like 83% of these people are going to be losers. They're going to lose money to me, right? So it really works out on the aggregate, and this is why a business like a casino, they spend tons of monies on flashy lights and advertising and trying to entice you to walk into their doors, because the more people walk through their doors, the more money they're going to win. And yes, an individual might win here or there, but on average, the individual is going to lose. And yeah, you can pretty much have expected earnings for something like a casino, which shouldn't make sense to people, but it does make sense because of the probability. This actually works out. And what happens is a good casino game is one where it sets it up so you feel like you can, oh, I just have to do this. I'm so close to winning, But they just make sure you're losing a little bit of money, right? They just give themselves a 51% advantage. So you're like, man, I feel like I can almost win. And you might win, but if 1,000 people play that game, they're going to lose, they're going to be ahead 1% per person on average. And ultimately, they end up pulling ahead. So expected value, very useful, very applicable, and it's used a lot of places. And you can kind of predict, at least on aggregate, how things are going to happen, how things are going to shake out. So that was problem 10. I just wanted to make sure you knew how to construct a probability distribution table and compute an expected value. Problem 11 is the next one, which is, it's very similar. I gave it to do 2 different groups. You have a different game. $5 is the buy-in, but this one is you select 3 cards at random without replacement from a standard deck. If you select the ace of clubs, the 10 of clubs, the 7 of clubs in any order, you win $10,000. Now, how's that for enticement? What? I paid $5 and I can win $10,000? Really? Okay. If you select 3 kings, you win $1,000. Otherwise, you lose $10. Sounds nice. I mean, this game, would you play it? No, I'm not going to play that game. Forget it. Right? I'm going to lose on average. But this one, what? I can pay $5 and win 10,000? Sign me up. Okay, let's do that. X. You play this game one time. How much can you win? What are the possible values here? Which group did this? Huh?
Group 4.
Group 4. What did you guys get here?
We had you could either lose 15, then 9,995.
So you could lose 15.
Yeah.
So that means you paid the $5 and you lost the additional $10. That means you come out $15 out of pocket. Yeah.
Then you could have 9,995, because it's the 1,000 minus the 5.
9,995. So you pay $5, but you win back 1,000. That's a possibility. So you'll actually be 9,995 richer, or
995.
995. So in this case you win 10,000. That case you win 1,000. That's a pretty deal. Doesn't matter, but whatever. Okay. How did you calculate the probability of these x's? What is the chance that you lose 15?
We had 0.99977.
Where did that come from?
We got that from the complement of the two other probabilities. Because it's like otherwise you lose 10.
Okay,
So we calculated the
but
other
maybe
two.
start with one of these then. Let's figure out what is the probability of you actually making the 10,000. How did you do that?
We did 3 over 52 times 2 over 51 times 1 over 50.
Okay, so to put this in here, you did what?
3 over 52 times 2 over 51 times 1 over 50. Because the order didn't matter, so you could choose the 3 cards in any order.
So if you select ace of clubs, 10 of clubs, or 7 of clubs in any order, you win $10,000. So order does not matter. So you're thinking of it how?
So you could choose any of the 3 out of 52 on the first one, and then 2 out of, since it's without replacement,
Okay.
and then there's 2 left that you could get on the second one, and then 1 last. But we weren't 100% sure.
Yeah, but is that without order though? Or is that equivalent to being without order? Like how do you reconcile that that is not a counting order? Because it sounds to me like you said something in order. Well, I could get one of them and then I could get the next one and then I could get the next one. Why, how does this take into account that I didn't care about order?
Because you can choose any of the 3, it's not just like one out of any of the 52.
Okay, so how are you counting your choices?
Because since it's without replacement, if you take 1 out of the deck, then like 1 will be gone out of the 3, and then 1 out of 52 will be gone, and the next one, and then another one.
So the denominator accounts for it? Is that what you're saying?
And the numerator, because if you choose 1 out of the 3, then there's only going to be 2 out of 3 left after you get it.
Okay.
That's the way we thought about it. I don't know if that's good.
Can someone think of another way to think about this? When you hear without order, what would you think? Yeah?
Well, I assume you're counting like the amount of outcomes for like picking picking an ace and then a 10 and a 7, it's like 13 choose 1 times 4 choose 1. Right? Like, kind of like if you're doing like a full house.
Yeah, but it's the ace of clubs specifically, so it's
Oh,
only
it's
one of the aces. So that's why there are 3 specific cards. So it's an ace of clubs, a 10 of clubs, or a 7 of clubs. So there are 3 specific cards in the deck. But order doesn't matter, so how do we normally think about that? 52 choose 3 would be the total choices. So I just want to make sure this is okay. So the denominator would be 52 choose 3. How do you know? Right. So you don't care about the order. You are selecting 3 cards at random without replacement. Okay. So how would you go about selecting? How many choices do you have? Yeah.
6.
How do you have 6 choices with this idea?
We could have the ace of clubs first, and the 10 of clubs, and the 7 of clubs. We could have 10 of clubs, ace of clubs, 7 of clubs, and then that would be it.
But you're doing order now, so. So there are 52 cards, I'm picking 3. Those are the total number of choices.
It would just be 1, because it's like all the ways that you can choose 3 cards. But then one of the ways that you choose all 3 cards has the 3 cards that you want. So 1 over if you choose 3. Like those are all the combinations of 3 cards.
Yes.
There's only one combination of 3 cards.
That has this.
Yeah.
Now,
choose.
so what does that actually simplify to? What does 52 choose 3 look like?
22, 100.
Huh?
1 over 22, 100. 22,000.
No, well, I just, actually tell me the formula for this. What would this look like? 52 choose 3, what is that? That's 52 factorial divided by 3 factorial and times 52 minus 3 factorial, so that's 49 factorial. So essentially what the denominator here is going to look like is going to be, well, 52 times 51 times 50 over 3 times 2 times 1, and if you flip that, what do you get? You get that, right? So that's actually equivalent. So we get 6 out of
It was 132,600.
come again?
132,600.
There's more than 1.
Like that?
Yeah.
So the proper way to explain this way of thinking about the problem would be that conditional thing that we did last time when choosing balls. So you'd have to talk about a conditional probability here. Probably if you're thinking about going directly from, in terms of the fact that you didn't have order, then you would talk about combinations. It's probably the way I would think about it. A couple ways to think about it, they're both right, but you have to understand what these numbers actually mean. Anyway, I suppose you did this one in a similar fashion?
Yeah.
What did you do for this one?
It was 3. No, sorry, 4 out of 52 times.
If you select 3 kings, you win $1. How do you figure out how many ways you would select 3 kings?
We had 4 over 52 times 3 over 51 times 2.
And how much is that?
1 over 50, 5,525.
Are you reducing or did you not?
Yeah,
reduce?
we reduced on both of them.
So this is 1 over
5,525.
5,000?
525.
5,520?
25. 25.
25. Did you reduce this one?
Yeah, to 1 over 22,100.
Like that?
Yeah.
Okay. And this one, how did you figure out this one?
We did 1 minus the 2 other probabilities added.
Complement probability. So you pretty much took the 1 minus the 1 over 5525 minus the 1 over 22100. And what do we get? What did you get here?
We got negative $14.36. Oh, sorry for the benefit.
No, the probability.
Yeah, 0.99977.
You didn't write it as a fraction? 0.99977.
77.
I thought you'd write it as a fraction. I probably prefer it as a fraction. What is this as a fraction? Just type this in your calculator and give me the fraction.
2,095. Is it 22,095 over 22,100?
Come again?
Not simplified. Good, let me simplify.
It should be very close to 1. So what did you say? What did you get?
22,095
0.95.
095 over 22,100.
100.
100.
Okay. And what do we have here? Because it says express the probabilities as fractions, so you definitely want to put fractions
And
here.
one of those combinations.
So that's part A.
One combination.
B. What's our expected value here? We just multiply those and add them all together. So we get minus 15 times 22095 over 22100 plus 995 times 1 over 5525 plus 9995 times 1 over 22100, which is, I guess, give me as a decimal now,
We had $14, negative $14.36.
negative $14.36. Sounds fantastic. Sounds like a fantastic game, doesn't it? What? Pay $5 and I can win 10,000? On average, you're going to lose money playing this game. So, casino's not losing anything by putting this game down on the floor. They're going to make $14 off of each person who plays this on average if a bunch of people play. What else do we have here? 15.
Good work.
So this was group
Yeah.
5. So should you play this game? Very tempting. I mean, if you're going away for a weekend at Vegas, why not? Just put $5. Doesn't matter. But you shouldn't seriously go into this game like, I'm seriously gonna win $10,000. No, you don't wanna think that way, because chances are you're gonna lose. Okay. The honey badger is just crazy. Yeah, that's from the script. Okay. All right. There's an 84% chance that a honey badger doesn't care. it just takes what it wants. Assume the honey badgers are all independently non-caring, and suppose you manage to gather 55 honey badgers. What is the probability that all the honey badgers don't care?
Okay.
How did you guys actually do this?
So for A, it would be binomial probability.
Huh?
Use that
So
equation.
here, you should notice that it's a binomial. Why is it a binomial?
Because they're all independent.
Okay.
Like,
Like there's only two answers.
There are two options. Either they care or they don't care, right? And
so for A, that'll be for that.
no, there are three things you need for a binomial.
It's like repeating.
You're repeating the same thing, right? You gathered 55 honey badgers and you individually checked them. Do you care? No. Do you care? No. Do you care? No. Do you care? No. Right? You're doing this experiment over and over. You're finding out whether the honey badger cares or not, right? So you're repeating an experiment. There are only two options. They'll either care or they won't, and they're all independent because it's totally in between the problem. So you know, I can think of this entire problem in the context of a binomial probability. You have to have those three things in place. Okay, so A. Let's actually write down the probabilities here. So we're looking for the probability of don't care. So we need to know what is our N, what is our P, what is our Q.
So N is 55. With 55 steps, like
Yeah,
individual honey badgers that you're checking.
Yeah.
P is 0.84, which is the probability.
that's the probability that they don't care.
And then Q would be the complement of 0.84, which is 0.16.
And so let X equals the number of honey badgers that don't care. Okay. So A. What was A asking for?
Probability that all of them do not care.
What is the probability that X equals 55? Right? What if all 55 don't care? What is that?
55, choose 55, which is 1. And then times 0.84 to the negative power. And then times 1.16 to the 0th power, which is also 1.
Okay, so this just comes down to all of them in succession don't care, so it's this doesn't care, and that doesn't care, and that doesn't care. 55 times in a row. Since they're independent, we just multiply all these probabilities, and that is going to be
0.0068%.
percent. It's a very small percentage. Odds are all the honey badgers ain't gonna care. B.
So use the same equation, and then except x is now 42, exactly 42.
What is the probability that exactly 42 don't care? So it's X equals 42. And that is going to be 55. Choose the 42 that's not going to care. What's the probability that they're not going to care? Well, 0.84 to the 42 times 0.16 to the, huh? 33?
Or 13.
13? What's that?
0.000026.
Thank you.
4 zeros?
Oh,
No,
no,
that's
that's the
next
wrong
to
one.
4.6.
1.315.
Yeah.
Okay.
Okay. C. Now, once you kind of figure out it's binomial, as you can see, it's kind of just a follow your nose kind of thing. For C, what is the probability that you care about here?
X equals 28 plus.
What was the range?
It's a range, so your X is between 28 and 30, but we know we can compute that by X equals 28 plus X equals 29 plus the probability that X equals 30. And that would be 55, choose 28, 0.84 to the 28, 0.16 to the 27 plus 55, choose 29. 0.84 to the 29. 0.16 to the 26. One is going up while the other is going down. Plus 55, choose 30. 0.84 to 30 times 0.16 to the 25. And you add those all up.
And this one was 0.000026.
Percent.
Yeah.
Very small chance that between 28 and 31. Okay, on average, if you actually did this, how many do you expect to not care?
So, initially we used the summation equation to find that out, at least for value equation, except there's a shortcut for binomial probability questions. And so you can just multiply 0.84, so your p times the n, which is 55.
Yeah, so it turns out for binomial, and this problem is also an excuse just to for me to tell you one other useful fact. So if you have a binomial variable x, then the expected value of x is actually going to be n times p. And you can actually go through that table and do all those calculations. I think you guys just did it on your TI 9 or whatever you have. And you literally had it sum up 55 times. Oh, what's this number times that probability? What's this number times that probability? But eventually you'll realize that you're going to end up here, which kind of makes sense. The probability of a success is this percentage. If you're doing it this time, on average, you would expect this percentage times that number of times. So that's actually something that you can know in general. That is in general true. In statistics class, they'll probably prove this for you. I'm not going to prove it here because I'll need to do a lot of summations that you probably don't know at this point. And you'll know that the standard deviation, you don't need to know this, but it's the radical of n times p times q. You don't need to know that. For a statistics class, you need to know that. So in this case here, we'd expect 55. We would expect 84 of them to not care. So how many do we expect to not care? 46. Yeah. 46.2. 46.2 honey badger. Right? So on average, you gather 55 of these guys. 46, 47 of them aren't going to care. So what are the chances that a small number would care? It's not going to be that high. You do expect on average to find 46 of them that won't. Okay, the last problem, the big one. Okay, problem 16. Which group wants to answer this one?
We answer.
Yeah, Davin?
The
Maybe you can do part A and you guys do part B. Is that cool? Okay.
So for part A, we said that the probability of someone being able to donate to a blood type A positive would mean that they would have.
Oh, hold on, let me quickly read it. Okay, so we have 4 blood types in this problem. That's the scenario. Blood types O, A, B, AB, and the probability of having each blood type is here. So that's the frequency, right? So there's a 43% of people have blood type O, 41% of people have blood type A, 11% of people have blood type B, and about 5% of people have blood type AB. There's also a blood protein factor called the RH factor. It could be positive or negative. And 86% of people are positive and 14% are negative. So when you say, oh, my blood type is A positive, It means that your blood type is A with this particular protein factor. Okay. Now, here is how blood types are distributed across the population. For blood types A positive, O positive, etc., these are who they can donate their blood to, and these are who you can receive blood from, depending on your blood type. So, if you're an A positive, for example, you can donate blood to someone who's A positive or A B positive. And you can receive blood from anyone who's an A positive, an A negative, an O positive, or an O negative. Okay, so that's how you read that table. So, what is the probability that a random person can donate blood to a person with blood type A positive? So that's what we want. Okay, so probability of can donate. So this is probably 15, part A, probably can donate to A positive. Okay.
So we said that would be the sum, that would mean that they either had blood type O or blood type A. So we said it would be the sum of the probability of having O and the probability of having A. So then we add them together as 0.43 plus 0.41.
Where are we? Okay, so the person in question has blood type A and A positive, and you can receive from someone who has A positive or A negative or O positive or O negative. So that just means O or A. Now technically here, because it can have both the RH plus and RH minus, that kind of accounts for everyone in blood type O anyway, so you won't have to worry about that individually. And here you can worry about the plus and the minus. The A would cover both cases. Okay, so ultimately you just have to add these two probabilities, which is 0.43. Probability of O plus the probability of A. We know this is the case because blood types are mutually exclusive. You can't have more than one blood type. So that's 0.43 plus so that's 0.84. You guys did the same thing?
Yeah.
Okay, cool. So pick up with B. Okay, suppose a hospital needs 5 units of blood to give to a patient. They have blood type A positive. 8 people walk into the blood donation center, and each person can only give 1 unit of blood. What is the probability that at least one person would be able to donate blood?
I think 1 minus the probability that 0 people would be able to donate blood.
Probability that X greater than or equal to 1. So let X equals the number of people. Who can donate blood? So this is 1 minus the probability that no one can do it. And what is the probability that no one can do it?
Oh yeah, it's like a combination of
It's like the combination of A choose 0 times 0.84 to the 0 square. No, it's 0.16 to the
Point
16 to the 8.
Right, so it means that this is the probability that they're not that guy. And all 8 of them isn't that guy. Since blood types are independent, you just multiply 0.6 by itself 8 times. So that's the probability that no one is going to have the blood type. And then you just do 1 minus that. That was what?
We turned in our answer.
Okay. Whatever that is.
It was 99.9996 or 9996.
996%, something like that?
Yeah.
Okay, so what is the probability that the hospital will be able to obtain all the blood that it needs?
Okay, so there's one. So the hospital will obtain all the blood it needs if X equals 5, 6, 7, or 8.
Okay.
Those are all independent because you can't have 5 and 6 or 5 and 7. So you can just add them.
Mutually exclusive. Yes.
Or, yeah, that's what I meant. So,
How do you find the probability of each one?
so for each one you do A choose X. So A choose 5, A choose 6, A choose 7.
Why are we doing that?
Because it's so there's a combination of 5 people.
It's a binomial.
Yeah, it's
Binomial. Yeah, you guys never even verified that yet. We didn't need to know that for the first one, but it is binomial. Because you're repeating an experiment, you're testing people's blood to see if they can donate. It's independent because blood types are independent, and there are two options. Either they can donate or they can't. So they either have the right blood type or they don't. So it's actually a binomial. And so here, pretty much we want the probability of X equals 5, or X equals 6, or X equals 7, or X equals 8. And each of these are the combination formulas. So it's 8, choose the 5 who can donate. The probability of them being able to donate is 0.84, and the probability of them not being able to donate is 0.16, and that would be 3, plus, of course, finally you get up to 8, choose 8, probability of 0.84 raised to the 8 times 0.16 raised to the 0, and that is
97.33%.
97.33%. So there's a good chance that we'll be able to save this guy who needs 5 units of blood. What is the probability that they'll get exactly the amount of blood that they need?
The probability that X equals 5.
Right, it's just this one. Right? So here, this counts for the situation where they get more than enough. They have what they need plus extra, right? But to have exactly what they need is just the probability that X equals 5. So it's 8, choose 5, 0.84, 5, 6, 8, and that was what?
9.59%.
What?
9.59.
9.59?
Yeah, I know what
So hopefully that clears up any confusion that might be going on. I'm not really going to do the rest. Next time I see you guys, we're going to go jump into a totally different topic. But try the rest of the problems here to kind of test your probability knowledge. There's just a mixture of things going on towards the end of probability, and should be a good indicator of what you need. I will see you guys on Tuesday.
I moved it to